Right. Next, I'd like to look at Bernoulli's equation, and this is a more generalized form for the pressure expression that includes the pressure at depth relationship that we had looked at before, but also takes into account the possibility that the fluid medium is moving. And if the fluid is moving, that means that there's a velocity of fluid flow in that region. And so to encompass all of these different possibilities, we have what's called Bernoulli's equation. And so that has several terms that, in a sense, might look a little bit similar to the conservation of energy expression. Although here, the units for pressure are energy per unit volume, which we can see by looking at a Pascal. That is a Newton per meter squared. And so if we think of that then as being the same as a Newton meter per meter cubed, then that's going to be a joule per meter cubed. So the units of pressure are the same as the units of energy per volume. And so if we think of it that way, then P1 at some point in a continuous connected fluid would be the internal energy per unit volume, and that would just be the internal pressure of the fluid, which could be measured by a pressure gauge at a particular point in the fluid. We could call that point 1 in the fluid. So here we might have, for example, point 1 in the fluid, and then out here we might have point 2 in the fluid. Okay, so this is a continuous connected fluid, but we have two different places in that same fluid medium which might have associated with them. Say this were a bathtub, then this might be the velocity of fluid flow at the upper surface, and this might be the velocity of fluid flow out the drain. Okay, so that would be like your P1 and your P2. And so here, this would be, in this case, that would be the pressure that's being exerted by the atmosphere here, and then P2 would be the pressure of the atmosphere exerted out here, which would cancel. But in some problems that involve airflow, the pressures don't cancel. Okay, so it depends on what kind of a problem you're dealing with, how Bernoulli's equation is going to be applied. And so we'll look at examples then of how to apply it for a liquid fluid, and then also for a gaseous fluid. Like if an airplane is flying through the air, then we could use Bernoulli's equation to understand how the airplane flies. Okay, so this is our internal energy at some point 1 in the medium. This is the kinetic energy per unit volume. So that's basically how fast the fluid is moving in a unit of volume. And rho g y1 is very much like a potential energy per unit volume. Because you notice here, this looks like 1/2 mv squared, but mass over volume is density. And then this looks like rho gy, that looks like mgy over volume. So that's potential energy per unit volume. And so then that would be equal to the pressure and the velocity and the height of the fluid column, essentially, at some other point in the medium. So if V1 equals V2 equals 0, then essentially we have our pressure at depth expression, P1 plus rho g y1 equals P2 plus rho g y2 at 2 points in a continuous connected fluid. Okay, and so for this problem, let's look at an example where we are sucking water out of a straw. Okay, so we learned before that the pressure is only related to the height of the fluid column. And so we could call this point here y2 equals 0, just as if this were like an energy problem. And then this top point in the fluid is what we could call y1. And let's say that up here you have your mouth, and the pressure in the mouth in order to suck water out of the straw. So here you are getting ready to draw that water up out of the straw into your mouth. Pressure in the mouth that you evacuate a little bit is equal to, in this case, 0.9 times P atmosphere. So in other words, you're able to draw enough air out of your mouth so that the pressure in your mouth is 10% lower than the atmospheric pressure. Then down here at this bottom point, we could say that if this is point 2 in our continuous connected fluid, this is point 1 our continuous connected fluid, then at this point the atmospheric pressure is exerting forces like this. The forces that are exerted by P atmosphere are basically driving the fluid into your mouth. Just like if you had a big foot and you're putting it down onto a brake pedal and that was forcing fluid up into some other region. Okay, and so the atmosphere then pushes this fluid up, but then that couldn't happen unless the mouth was at a lower pressure than the pressure that's exerted by the atmosphere down here. But because you've drawn air out of your mouth, then that pressure is lower than the pressure at this point. And so we could look then at this equation. We could see that Y2 is equal to 0, and we can see that P2 is 1 atmosphere, which is about 10 to the 5 pascals. Okay? And then P1, the pressure at point 1 in the fluid, is 0.9 times 10 to the 5 pascals, because it's 9/10 of atmospheric pressure. And so then we could ask, what is the maximum value for Y such that water will flow through the straw? You might wonder then, does it matter what the shape of the straw is? No. Remember before we saw that pressure at depth was just pressure at the surface plus rho gy. It didn't depend on the shape of the fluid column. And so here it doesn't depend on that either. It just depends on the height of, in this case, your mouth and the height of the straw vertically above the glass of water that you're trying to drink out of. Okay, so setting this up then, we can say that P2 minus P1 is equal to rho gy, and then Y is Y max, Y1 is equal to Y max. That's our maximum height of this fluid column. And so then that gives us 1 atmosphere minus 0.9 atmospheres is 0.1 times P atmosphere equals rho. That's the density of water, okay, because it's water that's in this, or it could be some kind of soda drink, but it would still be essentially the density of water. And so that would be rho g Y max. Okay, so we could solve this for Y max, and that would equal 0.1 times P atmosphere, 10 to the 5 pascals. Remember, it's 1.01 times 10 to the 5, but I'm rounding it off here to 10 to the 5, approximately, to a 1% error. And then that's divided by rho, which is 10 to the 3 kilograms per meter cubed, times g, which is roughly 10 meters per second squared. Okay, so this gives me 10 to the 4 divided by 10 to the 4, which is 1 meter. So that's interesting then. You should be able to draw water out through a straw if you're 3 1/3 feet above the glass of water, if you could evacuate your mouth by 10%. Okay, now that is not going to be easy to do, but if you could do that, that means that you could draw water up through that distance. Now, what does this mean for astronauts on the moon? Can they drink water out of a straw? The answer is no, because there's no atmospheric pressure. That's what's happening here, is the atmospheric pressure is exerting forces, just like if you were pushing down on a foot pump. That drives the fluid, pushes the fluid up into your mouth. And so pushing down drives the fluid up. So what you would have to do then is make up for that on the moon with a squeeze bottle. So that squeeze bottle then would take the place of the atmospheric pressure pushing down on the surface of the fluid and then could drive the fluid into your mouth. What about a barometer? Well, with a barometer, it's basically the same setup, but with zero pressure at the top of the barometer. So at the top of the barometer, you could have a pressure equals 0, and then the height of this barometer then could be a value y that could measure the, basically, the the amount of pressure that the atmosphere is pushing on this surface. Okay, so again, the atmosphere is pushing down like this on this surface, and then that drives the fluid up into this region. Okay, and so you could try this with a water barometer with the pressure up here being 0, and the pressure here at this point, 0.2, is P atmosphere, whatever the atmospheric pressure happens to be. But then you make it 0 up here by evacuating this region so that there's no pressure up there. So instead of in the mouth here having 90% of atmospheric pressure, here you've got 0 pressure in a barometer. Remember that a barometer measures atmospheric pressure by the height of the barometer. So let's try this with a water barometer. With a water barometer, then you would have P2 equals P1 here, or I'm sorry, let's see, what were we calling this? Yeah, P2, good. So that's our P2 down here. This is P1 is 0. So we have P2 just equals P1 plus rho g y. Okay, and so y2 is 0 at this point, and y1 equals what I'm calling here y. So that's the height of the column. But P1 is 0 because the pressure at the top surface is 0 because we've evacuated that region. And so this gives us then y equals atmospheric pressure, whatever that is, divided by rho g. Okay, and so let's plug in P atmosphere as 10 to the 5 pascals divided by the density of water. So that would be 10 to the 3 kilograms per meter cubed times g, 10 meters per second squared. So that gives us 10 to the 5 divided by 10 to the 4, or 10 meters. Okay, so a water barometer then is certainly something that we could make, but you would need to have a height of the water barometer that would go up 33 feet. So if you had one then, you go, well, what's the barometric pressure, say for a lab or something? You'll go, oh, I'll be right back. And then you go up 3 flights of stairs to see what the height of the water barometer is on the 3rd floor. Or if you're in just one floor, like we are here, you'd be up on the roof and then maybe using a telescope to see what it looks like. And so that's really not very practical then, to have a water barometer that's so big. So we might wonder then, well, is there any other kind of a substance that we could find on the Earth that is more dense than water, but is also a liquid at room temperature? I know, mercury, although we're getting rid of all our mercury barometers now because they're toxic. But, and we have other computer methods for determining barometric pressure that work just as well. But historically, at least, if we use mercury, let's try that over here, we'll just change the density of the fluid. So the density of mercury has a specific gravity of 13.6, and so that means it's 13.6 times the density of water, or 13.6 times 10 to the 5 pascals. And if I'm going to be really accurate here, I'll say times 1.01, because I want this to be exact for this particular calculation. 10 to the 5 pascals. So if that's the density of mercury, then we can go back and for a mercury barometer, the height of the mercury barometer then is going to be P atmosphere, whatever that is, divided by the density of mercury. I'm sorry, this should have been 10 to the 3. Kilograms per meter cubed. Okay. And then P atmosphere is our 1.01 times 10 to the 5 pascals. Okay. So now we've got it fixed. P atmosphere is this exact value, and the density of mercury is 13.6 times 10 to the 3. So that'd be times the density of mercury, 13.6 kilograms per meter cubed, times G, and here I'm going to use the exact value for G too, because I want an exact value for the height of the mercury barometer at 1 atmosphere's pressure. So if I plug that in, that's 1.01 times 10 to the 5 pascals, I get 0.76 meters. And so is that something that we can fit in a room? Well, yeah, it's less than the length of a meter stick. It's about 3/4 the length of a meter stick, or that's 760 millimeters of mercury. So sometimes we use that as a unit of measurement for atmospheric pressure. We do it in terms of millimeters of mercury, or we do it in terms of atmospheres, or we do it in terms of pascals. Or we can also do it in terms of PSI, pounds per square inch. So we've actually got several different methods for determining the same thing, which is the pressure. But it turns out that the 760 measurement is often used in a sphygmomanometer, which is a blood pressure machine. And so when you say that you've got a blood pressure of 120/80, you're talking about millimeters of mercury. So it's important that we do have some familiarity with PSI and millimeters of mercury, even though normally in a problem like this, we would be solving for it in terms of the number of pascals. Okay, so that takes care of atmospheric pressure if the fluid is not moving. But now let's take a look at what would happen if we've got a moving fluid. And so if we, for a moment, can look up at the data projector, show you a couple of pictures that are associated with, first, Bernoulli's equation, in which we have a connected fluid here, but there's a difference in height that is associated with the height of the fluid column, and there's also a possibility of different areas for the fluid element, if this, say, were a tapered pipe. And so we'll be looking at a lot of different examples of applications of Bernoulli's equation as we go. But in this one, I want to look at an airplane wing. Okay, so in an airplane wing, basically what you have is a curved wing surface that is more curved on the top surface than it is on the bottom surface. And you can also get those ripples or those streamlines of air to deflect even more by changing what's called the angle of attack of the wing with respect to the horizontal. And so that can give you even more lift. And so let's see how that would work then as an application of Bernoulli's equation. So in airplane flight then, let's not worry too much about the angle of attack. Now if the upper curvature and the lower curvature are the same, there actually are wings that are made like this, but they're basically just stunt planes. Okay, because in a stunt plane, a lot of times you need to fly upside down. And so if you fly upside down, then having the wing curved to enhance upward motion is going to also work against you, and it's going to tend to make you want to crash into the ground because it'll tend to make you want to drop. And so they just use the angle of attack to change the streamlines in a stunt plane. But here, let's say that we're not so reckless, and so we're going to just have a lower curvature on the lower wing surface, a larger curvature on the upper wing surface, so that as the streamlines of air move along the upper surface, and we can call this surface 1 here, and then also along this lower wing surface, we'll call this surface 2, we have a different velocity of airflow. So here V1 is going to be a faster speed than V2 down here. V1 greater than V2. Why? Because the molecules have to travel a larger distance but in the same amount of time. Why the same amount of time? Well, because if these molecules get to this point before these molecules get to this point, that would create a negative pressure region here. But a negative pressure region will automatically tend to draw in air. And so that will ensure that the elements of the atmosphere get to this point traveling this path and traveling that path at the same time. So V1 is greater than V2. Okay? And we also have a pressure that's associated with the velocity down here. We can call this P2. Turns out that pressure is going to be larger than the pressure up here. It's P1. And so this is really atmospheric pressure in the vicinity of a fast-moving fluid. And so P2 and P1 then are not canceling here, but are really the difference between P2 and P1 is what causes the lift force. Okay? And so then we also have a rho gy term on both sides. But here if we call this Y2 from some convenient reference position and this Y1, we can say that Y1 is approximately equal to Y2. And so the difference between them is small. And also, the rho gy terms are small because the density of air is small. Okay, so Y1 is approximately equal to 2 and rho is small. Now rho is also in the velocity terms here, but the velocity is big, and then it goes like the velocity squared. So that's really big. Okay? And so because of that, we can throw out these rho gy terms for airflow. Okay? Just because they're small in relationship to these other terms. That won't be the case when we get to a liquid fluid. But for a gaseous fluid, we can throw out the rho gy terms. So it's important that you internalize which application of Bernoulli's equation you're using. So for airflow then, we can say that P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. And then we can get the pressure difference between the upper and the lower wing surface. So that's just P2 minus P1. That's delta P, difference in pressure, from Bernoulli's equation is just the difference in the squares of the velocities. Okay, so this would be 1/2 rho V1 squared minus 1/2 rho V2 squared. We know that this is a positive value because V1 is greater than V2. And so then the forces that are associated with these different pressures are going to act perpendicular to the wing surface. So you've got this force here acting on the lower wing surface. We call this F2. You've got this force acting on the upper wing surface. That's a smaller force. It's F1. And so F2A minus F1A is the same as P2 minus P1. Okay? And so that's just equal to P is F over A. So this is going to be F2 over A minus F1 over A. There. And so that'll be equal to 1/2 rho V1 squared minus 1/2 rho V2 squared. Or the difference in force, which is equal to your lift force, is equal to 1/2 rho times V1 squared minus V2 squared times the area of the wing. Now, is this the total wing surface area? No. A is either the top or the bottom wing area. But not both. And more specifically, because you can see here from this curvature that the areas would not quite be the same. What we're really talking about here is the shadow of this area onto some surface. So say if you had the sun shining directly from above, it'd be a cross-sectional area of this wing, which would be essentially the area of the shadow of the wing. Because remember, the pressure forces here come in perpendicular to the surface, but the sideways components cancel, unless you think in terms of the effective wing area as being the cross-section. Then it's only the vertical component that's going to contribute, and you already know that the horizontal components are going to cancel out. Okay, and so that area is the effective wing area on the upper and lower wing surface, or the shadow of that area, and so therefore you can consider those to be the same. And they wouldn't be that much different anyway, because the curvature of the wing is relatively small. So let's say then that we have the weight of the plane, and everything that's in the plane is equal to 10 to the 4 newtons. The surface area of the wings is 10 meters squared. The density of air is equal to 1.26 times 10 to the 3 kilograms per meter cubed. Now the density of air will depend on how high up in the atmosphere you are. So, but we notice here how much smaller this is than the density of water. Density of water is 1,000 kilograms per cubic meter. Density of air is just maybe 1.2 thousandths of that. Okay, and so this doesn't mean that air is completely weightless. If you have a refrigerator filled with air, that would weigh about as much as an orange that's sitting in the refrigerator. Okay, and in a room the size that I'm in right now, all the air in this room might weigh about as much as I do. Okay? And so air is not completely without mass, but the density is way, way smaller than water. And that's why our applications to the fluid equations are a little different when we're talking about air versus when we're talking about water. Okay, so getting back to this problem then, let's say that V1, the velocity over the upper wing surface, which we know has to be bigger than V2, is equal to, in this case, let's say it's 400 meters per second, and V2 over the lower wing surface is equal to 380 meters per second. Okay, and let's ask the question then, will the plane fly? Well, to determine whether the plane will fly, it's not just enough to get a positive lift force. We have to realize that the lift force has to be greater than the weight of the plane. So this is delta F, which is equal to F lift. But a necessary and sufficient condition for airplane flight is that F lift is greater than the weight of the plane. So that's what we're going to check here. If the weight of the plane is 10,000 newtons, or about a ton, 2,000 pounds, then let's go ahead and plug in these numbers and see what we get for delta F. So delta F is going to be 1/2 rho, 1/2 times 1.26 times 10 to the, sorry, this is just 1.26, whoops, kilograms per cubic meter. So that is way less than the density of water, which is 10 to the 3. That's what I was saying. But I wrote in the 10 to the 3 here. So this is kilograms per meter cubed. So this is just this tiny amount versus 1,000. Okay, so that's what goes in here. Glad I caught that. Kilograms per meter cubed times V1 squared, that's 400 meters per second squared, minus 380 meters per second squared. So the difference in the square of the velocities times the wing surface area, which is 10 meters. And so let's knock that out and see if the plane is going to fly. I think it is, because I made these velocities pretty high. All right, so that gives us 9.82 times 10 to the 4. Newtons. So we've got 9 times as much lift as we need to overcome the weight of the plane. So we have no problems then with this kind of a velocity. But what if we change the velocities now so that this number is still, the difference is the same, but let's keep the velocities lower and see what happens then. So let's try this now with V1 equaling 100 meters per second and V2 equals 80 meters per second. So you might think, well, the difference in the velocity is the same, so therefore we would have the same lift force. But no, because it goes like the square of the velocities. So now this new delta F prime I could call it, would be 1/2 times 1.26 times 100 squared minus 80 squared times 10. That just gives us 2.2 times 10 to the 4. Newtons. So it would still fly because it's greater than the weight of the plane. But what if I had here for the weight of the plane 5 times 10 to the 4 newtons? Then in this case, it would be nowhere near being able to fly. And in this case, it could fly fairly easily. Okay, so if the weight of the plane was, say, 10,000 pounds instead of 2,000 pounds, which might be a little more reasonable for the weight of a plane, then a plane that has slower velocities has less square of the velocity. And so that's why little planes don't need a big runway, but big planes do. Because big planes have to lift a heavier load, and so they have to get going faster. And what that does then is that enhances the square of the velocity and allows for bigger planes to be able to take off even with a lot more weight.